Yes, thank you very much. I hope you can see my presentation now. Yes, so my name is Tonje Rubeck, and I'm a senior research engineer and product lead here at TICRA. And today I'll be talking about how we here at TICRA enables new frontiers for satellite payload antennas by providing design software for the satellite industry. A brief introduction. So as we wrote in the abstract for this presentation, TICRA is enabling the design of new satellite antenna concepts by developing software tools targeting specific promising candidates for the next generation payload antennas. And what does this mean that we are developing software tools targeting specific promising candidates? Well, typically you will have your general purpose solvers. They will typically use full wave methods such as the finite difference time domain method or the method of moments, and they'll apply the same algorithm to solve any electromagnetic problem you want to solve in that program. And they'll typically also have some general purpose optimization algorithms in there. It means that they are not particularly bad at anything, but typically it also means that they are also not particularly good at any particular set of problems. So what we have been doing here at TICRA for a very long time is to develop specialized simulations tools. These are tailored to model specific types of antennas. So this could be reflectors, reflectarrays, feed horns, or other types of antennas. And this means that we can take advantage of pre-existing knowledge of the simulation problem. So for example, we can use PO for solving reflector problems. We can do special things when we analyze reflector arrays and so on. And also it means that we can include tailored optimization goals and algorithms in our program that are specifically made for solving a certain type of antenna problems. And this means that we can make them very, very efficient compared to the general purpose tools. So in this presentation today, I'll give a brief overview of TICRA software, which is also available through this Altair Partner Alliance. And then I'll go through 3 cases of software that we have developed for specific payload antennas on satellites. So these are the reflector arrays, then it's for high throughput satellites, and finally it's for large unfurlable reflectors. So a brief overview of TICRA software. So TICRA was founded back in 1971 in Copenhagen in Denmark because the European Space Agency needed someone who could set up reflector antenna analysis and provide this as a service to the European Space Agency. This led to us in 1976 releasing the first version of GRASP, which is a specialized tool for exactly this purpose, design and analysis of reflector antennas. Up through the 80s, it became more and more desired by the antenna providers to have contour beams from their reflectors. So this means that you could make a shaped beam like what we see down here, so that you only cover a certain part of your the part that you're actually interested in. Here it's the US. And in 1988, we released the first and still the only commercially available piece of software for this particular problem called POS. In the late 80s and up through the 90s, we also got more and more into modeling and designing rotational symmetric feeds for reflectors. And in 2001, we released a specific software for this purpose called JAMP. And this was the first version in 2001. In 2006, we then released a method of moments add-on to GRASP, which allowed you to model your installed performance. This particular method of moments was highly adapted to solving large problems, as we see when we have an antenna placed on a satellite, as we see here. And this really was the specialized purpose for this MOM add-on in 2006. Around the same time, so in the mid-2000s, we started looking at the reflector arrays and transmit arrays. And in 2019, we released a product called QUPES specifically for this purpose. And this was also the first year where we released our new software framework called TICRA tools. So TICRA tools is a common framework for all of our software products for antenna design. It consists of these 6 products. So we have reflectarray antenna or reflector antennas in GRASP. We have the platform scattering and general scattering problems in Esteem. We have feeding waveguides in Jam3D. We have QUPES for these quasi-periodic structures, so reflector arrays, transmit arrays. Then we have POS for what we call advanced payload features. This is primarily shaping of reflector antennas and optimization of array excitation coefficients. And the latest product that we have added to TICRA tools is the uncertainty quantification, which allows you to quantify how much different distortions in your antenna will affect your performance. So these are the 6 tools that we provide inside of TICRA tools, and they are available through the Altair Partner Alliance. So the first case I'm going to look at is the reflector arrays. So reflector array and transmit arrays are typically seen as an attractive solution for antennas for satellites because they have a low stowage volume, because they are completely flat, so you can stow them very efficiently, and it's possible to steer the beam and make polarization dependent shaping of the beam by simply changing the pattern on these reflector array panels. The drawback with these compared to your standard reflector antennas is that it's hard to get a large bandwidth in this type of antennas. For this particular type of antennas, we have developed the software product QUPES. How this is built is that you set up your analysis on element level, and here you define what do you actually want to vary when you set up your element. So what should be the variable dimensions in your element? Here it's a length of one of these triple dipoles that we vary, and then we see that we get a nice phase curve covering the full plus minus 180 degrees. You then take that element and you put it on a surface to get your actual reflector array or transmit array, if that's what you're doing. And then you put it into an optimization where you specify optimization goals directly in the far field from this antenna. The benefits of using this approach is that it's very fast for optimizing element layouts on even very large reflect and transmit arrays. So you can have tens and even hundreds of thousands of elements. And it's very easy to optimize for even complicated pattern requirements because you specify it directly in the far field. So you can simply say, I want this beam width, I want to suppress these side lobes, and so on. So this is really the power that comes from this dedicated tool. As an example, here we have the Mascara project. This was a project we ran with ESA and Airbus. It is an array for synthetic aperture radars. It comes with 9 identical sub-arrays that are created out of these reflector array antennas. So we have a feed down here, then we have the sub-reflector up here, which is just a metallic plate, and then the reflector array down here. It has 2 separate modes, as they call them. It has a high resolution mode where they want 1.2 degrees. So that's the X polarization, and in the Y polarization, they want 2.4 degrees as a half power beam width. So different beam width in the 2 polarizations. Each sub of these reflector array panels contains of more than 70,000 elements, and we then put that into our system. Each element is like this, and we then vary the length of these arms of the Jerusalem cross down here. And this means that we have 140,000 variables on our panel here, 3 frequencies, and we can optimize this in less than 4 hours using this tool. So what we do when we have created this element and put it across our antenna is that we set up an uncertainty quantification analysis of it, just to make sure that the accuracy that the PCB manufacturer can deliver can actually live up to what we need. So here we have investigated 2 different tolerances of plus minus 50 microns and plus minus 20 microns. And if we look at this, here we have the 50 microns. You can see that we start seeing some uncertainty out here given by the red region around the red line, which is the nominal design. And similarly, we have it over here for the 20 microns, and we see that the uncertainty on the 20 microns is significantly lower than the 50 microns. And all of this is done using our UQ analysis, and it can do it on a full reflector array in just 30 minutes, as you write up here. So, so this is a very useful tool. We then built the reflector array and had it measured. So here we have it. The feed is down here. Here is the reflector array panel, and up here is the sub-reflector. Same over here, sub-reflector, reflector array, and the feed you can see down here. We then measured it, and as we see here, these are comparison with the measured and simulated results, and each contour on this plot is -5 dB, so -5, -10, -15, -20, and so on, from the peak value, and we see that there is a very good agreement between the simulated and measured results. So QUPES can really do accurate and quick simulations and optimizations of such antennas. The next example I'll go through are some high throughput satellites. So what is a high throughput satellite? Well, basically, instead of having one large coverage area where you send down a contour beam, we move over to a different kind where we have cut our frequency band into 2 separate subbands, and then we use 2 separate frequencies. This gives us a total of 4 combinations of frequencies and polarization. And you can then lay out small beams across your coverage area instead of one big beam. And this means that you can get a much higher throughput through your satellite than just having a single beam. There are different architectures for this, and they require slightly different modeling tools and optimization tools. A typical single feed per beam will have 4 reflectors, each of them generating one of the what we call colors, so one combination of polarization and frequency. You can have multi-feed per beam, which can either have still 4 apertures like we have down here, or go down to 2 apertures. And what we see more and more is that you get adaptive phased arrays, antennas either in array-fed reflectors or in direct radiating arrays, and they will typically be an architecture something like this. So you have a lot of transmitting elements in your array, and each of these amplifiers, perhaps they can give you 5 watts, and you have 1,000 elements, but so that's 5,000 watts in total, but maybe your satellite can only deliver 2,000 watts. So this means that even though your elements can go up to a certain level, you have to take into account that there are some higher level restrictions when you actually start doing the optimization of the array coefficients. So to meet these demands, we have extended POS, which started out mainly for contoured beams, but have now been extended to also be able to do these multi-beam antennas. We still have the efficient PO algorithms that we have had for many, many years in POS. And now we have then extended them with this advanced optimization of array coefficients, which works for both array-fed reflectors and direct radiating arrays. And in addition to this, we have included several optimization goals specifically for this type of antennas. Station files for generating complicated coverage areas, and also C/I optimization, so carrier to interferer optimization, which is also a requirement for these types of antennas. Yes, if we take a look now at the phased array fed reflector with an adaptive coverage, so typically you will have something like this. This is the Atlantic Ocean. The US is over here and Europe is over here. So at 0 UTC time, there's a lot of traffic on the east coast of the US, while at the noon UTC time, there's a lot of traffic over here in Europe and going starting from Europe going towards the Americas. So what you want is an antenna that at one time of day can have a coverage like this, where you have a lot of capacity along the east coast of the US, and then later in the day you will change it to something like this, where you have more capacity up here, where you have a lot of flights going from the Europe towards the US. So you can do this by simply putting in an array like this. So this is an array fed reflector. We have 192 elements. Each of them can deliver 18 watts, but the total can only be 930 watts. So this is the kind of constraints that you often see that you have to put into your optimization of these types of antennas. And then you put it into POS, and it comes out with beams that fit your requirements over here. So basically, this is the kind of things we have added into POS to be able to do this kind of adaptive phased array antennas. Another thing we have been looking at is how to reduce the number of apertures in antennas for this type of mission. So typically, you would have 4 single feet per beam apertures like this, generating your 4-color scheme. But now, if instead we go to something like this, where we have a dual polarized linear horn here, then our linear polarization hits our reflector. If we can make that go into 2 circular polarized beams that are slightly tilted compared to each other, we can actually, from a single aperture, create 2 colors of these beams. So basically, the A and the B beams up here. And to do that, we put an array or a reflector array on top of our reflector here. This is something we have done in a project that we did with ESA and MDA in Canada. So basically, each of these 41 feeds down here generates 2 of the beams up here, so 1 red and 1 yellow. So the required apertures now go down to 2 dual band apertures. So one of them covers frequency 1 in both receive and transmit, and the other one frequency 2 in receive and transmit. And then we optimize our system here. It has more than 54,000 elements across the surface, or more than 54,000 unknowns across the surface, 4 per element. So that's the rotation of these and dimensions of these elements that we have here. And we then built a model of this, a breadboard model. So this is the full reflector. This is a close-up of the surface where you can see the elements. This is the measurement setup. So we have one in the center, one displaced to the right, one displaced down here. This is a photo of the setup. And we can see that there is a very good fit. So this is in the TX band, this is in the RX band. Again, a very nice fit between measured and calculated. So measured is solid and calculated in dashed lines. And we also did it across the entire band for this feed 1. And we see again that there is actually a very nice agreement between measurements and simulation in this case. So the last thing I'm going to talk about is unfurlable reflectors. We see more and more interest in large unfurlable reflectors. This is both for telecommunication antennas for high throughput satellites. This is the AlphaSat mission that ESA was involved in. Over here we have the CEMIA radiometer. So this is an Earth observation mission where we also see a lot of interest for these types of antennas. And finally, we also see them for downlink antennas for small sats and CubeSats. So here the actual antenna in itself is actually not that big, but compared to the platform, it's still very big. So you still need to do this unfurlable antenna. To analyze this type of antennas, we have GRASP, which we have had for more than 50 years now. it's very fast and accurate to analyze these large surfaces using the physical optics algorithm, and it's also relatively easy to include non-PEC surfaces on your reflector. So if you want to model these mesh surfaces that you typically have on this type of reflector. In addition to this, we also see a lot of interest for the UQ product in these antennas, because typically you have a greater uncertainty on the surface shape than you have on your normal fixed reflectors. And this means that the accelerated algorithms that we have in the UQ product for modeling the impact of these surface uncertainties are very useful. And also, when you're actually defining the requirements for this type of antennas, it's very good that you can first model what is the impact of a certain surface inaccuracy before you actually put it into your requirements. Just a couple of examples here. So this is the CIMIA radiometer. It's a multi-band microwave radiometer that TICRA has been working on for quite some years now. It's a project run by ESA. So it has maximum frequency at 36.5 gigahertz and 7.15 meter reflector out here. And this is kept in place by 1,111 points where the reflector is fixed. So what we have done here is that we've done a PO analysis of the complete reflector, and then we have done a UQ analysis of the displacement in every single point on the reflector to see what is the impact here. And we see that there's very little impact in the main lobe here, but when we get down, say, some 30 dB or so, 25, 30 dB below the peak, there is a significant impact on the side lobe level down here. And this can be done in just 1,200 iterations with our UQ analysis, and in just over an hour. So even for this very large reflector, it's possible to do uncertainty quantification. My final example is a shaped mesh reflector, similar to what we saw before. So it's a 2.3 meter diameter with an FOD of 1.1, and the concept is that it should have high directivity in this area, and then a suppression out here to the west. And this is a picture of the antenna in the measurement facility down in ESA. And we have, again, the comparison between the measured and the simulated results. And we see that there is a very good agreement between the blue line, which is the simulated results, and the black line, which is the measurements. And similarly, if we look at a contour plot of it, there is actually both a dashed and a solid line in this plot, and we see that you have to get down to around 25 dB before you actually see a difference between the measured and simulated results. So again, a very good agreement between what we have optimized. So basically, we have done the shaping in POS, and then we have done the fine modeling in GRASP, and finally also added the steam to get impact from the rim here. And with that, we have been able to get a very good agreement between simulated and measured results. And with that, I've reached the conclusion. So we have been providing specialized antenna simulation tools for the space community for the last 50 years or so. Today, everything is collected in what we call the TICRA tools framework. It contains these 6 products, and you can get them through the Altair Partner Alliance. And by using these specialized tools, because they are so quick, it allows you to do optimizations, analysis that would otherwise have been basically impossible to do. And if you start combining the different tools, you can actually build a complete antenna system. Say, for example, taking a feed from Gen3D and illuminating your GRASP reflector, and analyze complete antenna systems that would not be easy to analyze using these general purpose tools. So I hope that with this presentation I have explained why it's sometimes good to move away from the generalized tools and move into the more specialized tools. And with that, I would like to say thank you.